Hello student, good morning. I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I am going to start new chapter, the D and F block elements. Last class I have finished group 18 of P block elements. Now I am going to start D and F block elements. Iron, copper, silver and gold are among the transition elements that have played important roles in the development of human civilization. The inner transition elements such as thorium, protactinium, uranium are proving excellent source of nuclear energy in modern times. The D block of the periodic table contains the elements of the group 3 to 12, in which the D orbitals are progressively filled in each of the 4 long periods. Again, I am telling you, the D block of the periodic table contains the elements of the groups 3 to 12, in which the D orbitals are progressively filled in each of the 4 long periods. The elements constituting the F block are those in which the 4F and 5F orbitals are progressively filled in the latter 2 long period. These elements are formal members of group 3, from which they have been taken out to form a separate F block of the periodic table. The names transition metals and inner transition metals are often used to refer to the elements of D and F block respectively. There are mainly 3 series of the transition metals: 3D series, 4D series and 5D series. 3D series means scandium to zinc. 4D series means yttrium to cadmium, and 5D series means lanthanum to mercury, Hg, omitting cerium to lutetium. The fourth 6D series, which begins with actinium, is still incomplete. The 2 series of the inner transition metals, that is the 4F and 5F, are known as lanthanoids and actinoid series. 4F and 5F are known as lanthanoids and actinoids respectively. 4F is known as lanthanoids and 5F are known as actinoids series. Strictly speaking, a transition element is defined as the one which has incompletely filled d orbitals. Incompletely filled d orbitals in its ground state or in any one of its oxidation states. Zinc, cadmium and mercury of group 12. Zinc, cadmium and mercury of group 12 have full D10 configuration in their ground state as well as in their common oxidation states, and hence are not regarded as transition metals. Question is asked: zinc, cadmium and mercury of group 12 have full D10 configuration in their ground state as well as in their common oxidation state, hence are not regarded as transition metals. However, being the end members of the three transition series, their chemistry is studied along with chemistry of the transition metals. The presence of partly filled D and F orbitals in their atoms sets the study of transition elements. Again, I am telling you, the presence of partly filled D or F orbitals in their atoms sets the study of the transition elements and their compounds apart from that of main group elements. However, the usual theory of valence as applicable to the main group elements can also be applied successfully to the transition elements. The usual theory of valence as applicable to the main group elements can also be applied successfully to the transition elements. Various precious metals such as silver, gold, and platinum, and industrially important metals like iron, copper, and titanium form part of the transition metals. Again, you listen. Various precious metals such as silver, gold, and platinum, and industrially important metals like iron, copper, and titanium form part of the transition metals. Here in these units, besides introduction, we will study electronic configuration, occurrence, and general characteristics of transition elements, with a special emphasis on the trends in the properties of first row transition metals and the preparation and properties of some important compounds. Now I am going to discuss details of transition elements, particularly D block elements. Transition elements means D block elements, and inner transition means F block elements. Then now I am going to discuss the transition elements means D block elements. First, we should understand position in the periodic table, where it exists. Position in the periodic table. The D block occupies the large middle section flanked with S and P block in the periodic table. Means between S and P, D block will come. The D block occupies the large middle section flanked by S and P block in the periodic table. Means between S and P. In periodic table, between S and P blocks, D block comes. The very name transition given to the elements of D block is only because of their position between S and P block elements. The D blocks of the penultimate energy level means before the last orbit. That energy level is called penultimate energy level. Actually, energy level and orbit both are same. The d orbitals of the penultimate energy level in their atoms receive electrons, giving rise to the 3 rows of transition metals. That is the 3D, 4D, 5D. Again you listen, the d orbitals of the penultimate energy level in their atoms receive electrons, giving rise to the 3 rows of transition metals. That is the 3D, 4D and 5D. The 4th row of 6D is still incomplete. Now I am telling you about electronic configuration of d block elements. In general, the electronic configuration of these elements is n-1 d 1 between 1 to 10 and last is ns square 1 to 2. n-1 d because it is incomplete may have between 1 to 10, sometimes 1, 2, 3, 4, 5, maximum 10 and minimum 1. Then n-1 d 1 to 10 n s square, but here maybe sometimes s1, sometimes s2. Then in general the electronic configuration of these elements is n-1. 1 is less penultimate energy level. n-1 d, and in d how many electrons is possible? Then between 1 to 10 and last is ns, and how many electrons? Then sometimes 1, sometimes 2, means 1 to 2. The n-1 stands for inner d orbitals. n-1 also stands for the inner d orbitals, which may have 1 to 10 electrons, and the outermost ns is the outermost orbital, may have 1 or 2 electrons. However, this generalization has several exceptions because of very little energy differences between n-1 d and ns. Means d and s energy differences are very less. n-1 d and ns energy differences is very less. Now other things I am telling you. First I told about that energy difference between n-1 d and ns orbitals is very less. Furthermore, half and completely filled sets of orbitals are relatively more stable. Half filled and fully filled orbitals are relatively more stable. A consequence of this factor is reflected in the electronic configuration of chromium and copper. In chromium d has half filled, means 5 electrons, and in copper that is d has 10 electrons. In 3d both comes under 3d. Then in chromium d5 and in copper it is a d10. Okay, and that's why in d5 and d10 are stable. Okay, stable electronic configuration. Now consider the case of chromium, for example, which has 3d5 4s1 instead of 3d4 4s2. Actually it should have 3d4 4s square, but actually it will have 3d5 4s1 means from the last orbital, which is 4s2, one electron came to the D, and now D4 became D5. Why? Because in D5 chromium will be particularly in D5 chromium will be stable. It is a half filled. D has 10 capacity of 10 electron, but 5 means stable. Half filled means stable. That's why one electron from the 4s square, one electron come to the D. Now D became, from D4 it became D5. Okay. Then in chromium 3D5 4s1. This happens because of stability. Okay. The energy gap between the two sets, the 3D and 4s of orbital, is small enough to prevent electron entering the 3D orbitals. That's why from the 4s electron is coming to 3D because energy difference is very less. Similarly, in case of copper, the configuration is 3D10 4s1 and not 3D9 4s2. According to arrangement of electron, it should be 3D9 4s square, but actually it will be 3D10 4s1 due to the same reason what I told you. One electron from the 4s comes to the 3D, which was having 9, now it became 10. Now D is fully filled, that's why it is stable, and copper in this way it is stable. Okay. Then this I told you, in case of copper the configuration is 3D10 4s1, not 3D9 4s2. The outer electronic configuration of the transition elements, now I am telling you. This electronic configuration, outer electronic configuration means last orbit. Then here for first I will tell the name of elements coming under the transition elements. First series. Then it start from 21 and it will last 30. Then 21 means scandium, 22 means titanium, 23 means vanadium, 24 means chromium, 25 means manganese, 26 means ferrous, 27 means cobalt, 28 means nickel, 29 means copper, 30 means zinc. Okay, this is the members of first series, elements of first series of D block, also called transition elements, in a ground state, not in excited, ground state. Then now this scandium, that is 21, then in 4s, 2 electron is there, and in 3D 1 electron is there. Now in titanium 1 will increase, 2 will be common, 4s will be 2 electron, 4s has 2 electron, but now in scandium 3D has only 1 electron. Then now in titanium, when it will come 22, 1 electron will increase, scandium is 21, titanium is 22, then now 1 electron increase, then it will go to the 3D, now it became D2. Similarly in vanadium, again 23, then again extra electron will go to the D only, then D3. Now in chromium, actually it should go D4, but now it will have D5. One more electron from the S, it will come to D, then directly means outer electronic configuration will become 1, 5. S will have 1 and D will have 5 because of stability, half filled. Now in Mn electronic configuration, this atomic number is 25. Then now 1 electron came. Then where it will go? Then it will go to the S. Now again S become 2. Only in chromium S is 1 because that 1 electron came to the D. Then D become 5. Now in manganese 1 extra electron, now it will go to the S. Then S will become 2 and D will be 5 only. Now iron 26, now extra electron, now it will go to the D. Now it becomes 6. And now cobalt 27, then now extra electron, new electron will go to the D. Now it became 7. S2 is the same. Now 6 became 7. Iron was 6. In iron D was 6. Now in cobalt 27, new electron will go to the D. Now it became 7. And nickel 28. Then now again new electron will go to the D only. Now it became 8. Now again you can see nickel 2 and 8 is there. 2 and 8. In copper 29. The new electron it will go to the D. Then it should be D9. But actually it is a D10. Now from the S 1 electron will come to the D. Then now 9 will become 10. And S will have only 1 electron. Then copper outer electronic configuration become 110. Just like chromium 1, 5. Now here is a 110. Okay. And now Zn, that is a 30. The new electron will go to the S. S was having only 1. Now it became 2. Then 2, 10. Then now you can see D is fully filled. D. And S is also fully filled 2. That's why Zn is not considered as transition because there is no scope for transition. S is also 2 and D is also 10. Then no transition. No transition can take place. Like chromium, you have seen 2 was there, then 1 came, then 4 became 5 in chromium, 1, 5. Then 1 and 5, there is possibilities for transition because S and 5 both are incomplete. That's why transition is possible. But here in zinc 210 complete filled, no transition possible. But copper 29 110 is there, and here possibility is there 1 and 10. S has only 1 electron, scope is there. Okay, that's why here up to copper means 21 to 29 continuously all are transition elements. But Zn is not the transition elements. Question is asked. Why? Because S2 and D10 both are fully filled. There is no scope for transition. But for the study point of view, Zn is kept because D is there, but D is fully filled. That's why only for study purpose it is kept under the series. Okay, first series. Now I am telling about the second series. Second series starts from 39 to 48. 39 to 48. Then first I will tell the name of elements. 39 is yttrium, Y. 40 is zirconium, Zr. 41 is niobium, Nb. 42 is molybdenum, Mo, small o. 43 is technetium, Tc. and 44 is ruthenium, and 45 is rhodium, and 46 is palladium, 47 is silver, and 48 is cadmium. Okay, again I am telling you Y is means 39 is Y, yttrium, 40 is zirconium, Zr, 41 is niobium, Nb, 42 is molybdenum, 43 is technetium, and 44 is ruthenium, 45 is rhodium, 46 is palladium, 47 is silver, means Ag, 48 is cadmium. Okay. Now you see the outer electronic configuration. Then just like first series, here also in second series also generally S will have 2 electrons, and D will start means 4D. In first transition it was the 3D, it started with 3D. Now in second transition it will start with 4D. Then S have 2 electrons and 4D has 1 electron, means D1. Now in zirconium, new electron means now 39, 40, new electron will go to the D. Now it become 4D2, and now Nb, next new electron 41. Then now it will go to the D. Actually it should be D3, but now 1 electron from the S is coming, and now it is becoming 4, and S is becoming 1. Why like this? Because this D orbitals is split into 2 groups. Okay, Eeg and T2G. It splits in 2 groups, Eeg and T2G. Then here in first group, Eeg in 4 electrons, it will be stable. It will be stable. That's why it happens that 1 electron came from S to D. Then now it was 3, now it became 4, 1, 4. Now 42 molybdenum, new electron again, now it will go to D. Now it became 5. D became 5. It has not gone to the S because of the half filled. This way also it is stable, and splitting wise this also 4 was stable. Okay. Then now in both cases, in 4 niobium, it was 1 and 4. Now new element means 42 molybdenum, now it went to the 5, new electron went to the D and it became 5, and S is till that 1 only, 1, 5. Now TC, technetium, okay, it is 43, and here new electron will again, it will go to the D only. Now it became 6, and S is till now it is 1 only. Why? Because of in this situation again this it is a splitting wise, as from the point of splitting, it also feels stable. 1, 6, 1, 7 also. Now new element, that is 44, that become again, it will go to the D only, 1, 7 only, and rhodium 45, again 1 electron one new electron will go to the D only 8, but S is only 1. It continuously 5 in 5 elements: niobium, molybdenum, Tc, Ru, Rh, Tc and Ru, Rh. Everywhere S has 1 electron, starting from niobium, Nb, Mo, Tc, Ru, Rh. Continuously 5 elements has 1 electron in S. Okay, this is only important, and D already well understood. 4, 5, 6, 7, 8. Now important thing is with palladium. Now rhodium is 45 is 1 or 8. 1 or 8. Now palladium 46. Then now 1 electron. It will go to the D. Then 8 should come 9. But it is not 9. It is a 10. Whatever 1 electron was there in S, that also came to the D. And now D became 10. Fully filled. Then due to the stability, this electronic configuration is preferred. Okay, 0, 10. Now S has no electron. S has no electron, 0. Now silver 47, 1 electron came. Then now it will not go to already D is a filled, D10, it is a filled. Then where it will go? Then it will go to the S. It will go to the S. Then now S become, it has new opened. S now opened. It was closed, now it opened. 1 electron. Silver 47, then 110. 110 is important. Question is asked. Now new electron 48. Cadmium 48. Then now where it will go electron, new electron? D is already filled 10. Then it will go to the S. Then now cadmium is 210. 2, S has 2 electron, D has 10 electron. Then that's why cadmium last, all 3 group, last element is not transition element. Then cadmium is also not transition elements. Why? Because there is no scope for transition. S is 2, D is 10. Hence no transition is possible between S and D. But in others it was possible. Then 39 to 47. 39 to 47, it is a transition element. 48, which is cadmium, and it is a S has 2 electron, D is 10 electron. Hence there is no scope for transition. Hence it is not coming under transition elements. Question is asked. Then silver electronic configuration, outer electronic configuration, I told you it is important. Okay. Second series, many question is asked from the second series, because this splitting of d orbitals. Okay, one orbital has this 2d and rest 3 orbital, 2d and 3d, means here 5 orbitals are there, you know. D has 5 orbitals. Then 2 orbitals will come under Eeg, and 3 will come under T2G. Okay, Eeg and T2G. Then that's why here only from the niobium onward all have in S11 only, and palladium 0 and the 10. But here 0 is there, means S can be opened, because only 0 is there. That's why it is coming under transition PD, but CD is not possible. And silver, new electron came, then it went to the S, opened, then 1 and 10. Then this I told you, last element cadmium, which is 48, is a non-transition element. Now third series, come to the third series. Then now I will tell the atomic number first and then I will tell the name. 57 to 80. Lanthanum is 57. Lanthanum is 57. But in series you will see in third series after the 57, 72 is there. 72 means 58 to 71. Where is it? It is not written here. After 72 it is there. 57, then 7 directly 72. 73 next, 74, 75, 76, 77, 78, 79, 80. 80. I will tell you where it went. Then 57 means lanthanum. 57 means lanthanum. La. Lanthanum. And after 57, 72 directly 72 is there. Then 72 means HF. Hafnium. HF. Capital H and a small f. La also, always you know that first letter is capital, small, and other letter is small. La. Lanthanum and 72 HF. Hafnium. And 73 is tantalum. Ta. Tantalum. And 74 is W. Tungsten. 74 is W. Tungsten. 75 is rhenium. Re. Re is rhenium. 75. 76 is osmium. Os. Osmium. 77 is iridium. Ir. Iridium. 78 is platinum. Pt. Platinum. 79 is auric. Auric means gold. Au. And Lt is Hg means mercury. Then now this lanthanum, after the lanthanum direct hafnium is there. 57, after 57 directly 72. Then from 58 to 71, where it went? Then it went separately, and that is known as lanthanum series. Separate. 58 to 71 is written separately down the periodic table, and it is called lanthanum series. Lanthanum series starting from 58 to 71. How many elements are there? 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 69, 70, 71. 14 elements. 14 elements. Okay. Then lanthanide series has 14 elements. And why it is kept separately? Because their properties are very similar, very similar. You can't write, you can say its place is the same. Place is same. Okay. Due to very close, I can say properties. Then this I have told you. Now come to the electronic configuration. Then like other two series, third series, that is the 6s and 5d is there. First series you have seen, it was 4s 3d. 4s 3d. Second series was 5s 4d, one less. 5s 4d. Now it is 6s 5d. Then now here again you will find same type. S will have 2 electron and D will start with 1. Then lanthanum, it starts with 1. D1. And after that hafnium 72. S is 2, but now next electron will go to the D. Now it becomes D2. And again 73, new electron will go to the D. Now it becomes D3. Again 74, tungsten, new electron will go to the D only. Then now it becomes D4. Rhenium, Re, Now new electron will go to the D only, 5. It became 5, 2, 5. Okay. And now here next 76. Then new electron will go again D only. Now it become D6. And iridium IR, new electron means now 77. New electron will go to the D only. Now it becomes 7, D7. Now here you can see new electron 78, platinum 78. Now here as usual, now it should go 8, D8, but now it is a D9, because from the S one electron came here and became 9, D9. I will tell you this now in S only one electron is there and D became 9, and new electron will now means 79 auric gold. Then now new electron will go to the D. Now it became D10. Okay, S is 1 and D is 10. And in Hg 80. Then now because D is completely filled, then now new electron will go to the S only, 210. Then both are filled. That's why Hg is not coming under transition elements. But here now auric we understood 1 and 10. That meaning we understood same way because this D is fully filled. D became fully filled. That's why it happened. But now in platinum 1,9 is there. Why 1,9? And here also you have seen that in 75 rhenium 2,5 is there, and before that 74, 75. Then S is 2, 74 is S, 74 S2, and D is 4. Here also, according to the previous concept, it should have become 1,5, but it is only 2,4. It is not become 1,5. And rhenium also it is a 2,5. New went only in D, 2,5. Then here question arises, why not like other series, why it is not 1,5? Tungsten 74, it is a 2,4. It should have become 1,5, but it is not like that. Why? Because now here F orbital also started. F orbital also started. Then due to its interference, it has changed the trend. It is not becoming like that. Only with this D auric 79, 110 only there. It is just behaving like other D. But here in platinum also 1,9 is there. 1,9 is there. Then here 1,9 it is not becoming 0,10. Not becoming 0,10, and in 74 tungsten it is not coming 1,5. It is 2,4 only. Then this is happening due to the this N-2F, N-2F, just like N-F ds was there. Now N-D, inner transition started. F already started. Due to its interference, this is not showing this trend like or behavior like when D was dominating. Okay, D was dominating. Now F also started, N-2. Then if you write electron configuration, then you find n minus 2 will be also there, n minus 1 will be also there, correct? N minus 2, n minus 1. Okay, then that's why it is called inner transition element, that is called F block elements. Now I am telling about the next series, third series I told you. Now fourth series, it starts with 89 and it will end with 112, 112. Okay, then here actually in this series again you will find actually its atomic number starts with 89, and after that 89 next is ruthenium, RF 104, 89 directly from 89 to 104. In the middle 90 to 103. Where is this? It is not there. Okay, its reasoning is again same. It is called actinium series. Mean 89, after the 89 it is 104. Then where is 90 to 103? Then these are actually written separately and it is called actinide series, and it is written in the periodic table after the lanthanide series down, it is written actinide series. It is also of 14 elements, means 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103. 14 elements is called actinide series, and actually all these elements have very similar properties, very similar properties. Okay, this is called actinide series, and these series are also called man-made. So many elements are made in a lab. Okay, man-made element. Okay, I will tell you especially for these two series, lanthanide series and actinide series. Then 89 is actinium. After that RF is there, ruthenium 104, and after that actually I will tell the name of these elements. All are you can say man-made element. Okay, then their symbol only I will tell you, and separately I will tell the name because the names are not common. It is man-made, but symbol I will tell you, and I will also tell the names separately. I will tell the names. Okay, because names are not common. Then 104 is RF, ruthenium, RF, and 105 is DV, and DV dash this DV. I will tell you all the name. It is in all the new name. I will tell all the name, just to wait. Okay, first let me tell the other names. Then AC is this is called actinium 89, RF 104, and DV 105, SG 106, and BH 107, HS 108, MT 109, DS 110, RG 111, and UUB, that is the 112, 112. Again I am telling you, AC 89, RF 104, DV 105, SG 106, BH 107, HS 108, MT 109, DS 110, RG 111, U and UUB, that is 112. And here outermost electronic configuration. Here now 7s 6d is there. 7s 6d is there. Okay. Then here again you will find same way electronic configuration. S will have 2 electron fully filled. S have 2 electron except 111 Rg. Okay. And reasoning is the same for Rg. And D start with 1 means 89 is D1. And next is 104. New electron will go to the D only. D, it become D2. Next 105 is D3. And next electron 106. That is the D4. Again 107. D5. 108. D6. 109. D7. 1110. D8. Means continuously all electrons are going to the D only. And S is only 2. Now 111 Rg there. Now as usual D is going to be fully filled, hence it should be 9, but now 1 electron from S came to the D. Now it became D10. Then S is 1 and D is 10. And last is 112. Then here next electron will go to the S only because D is fully filled. Now after coming 1 electron, S is also fully filled. Hence this is also not the transition element. Okay. This I have told about the these things, outermost electronic configuration. Now more I will tell you. Okay. I will tell the name separately. I will tell the name. All names are new. Okay. I will tell all names. Now just you know more about the electronic configuration. The electronic configuration of Zn, cadmium and Hg represented by the general formula n-1 d10 ns square. You remember these three last member of the three series, first series, second series, third series. Last three are common, that is the Zn, cadmium and Hg. Question is asked, that's why I am highlighting. The electronic configuration of Zn, Cd, Hg are represented by the general formula n-1 d10 ns square. The orbitals in these elements are completely filled in the ground state as well as in their common oxidation states. Therefore, they are not regarded as transition elements. The d orbitals of the transition elements project to the periphery of an atom more than the other orbitals. That is the S and P. D is dominating periphery of an atom more than the other orbitals. That is the S and P. Hence, they are more influenced by the surroundings as well as affecting the atoms or molecules surrounding them. Okay, this is a very, very important point. The d orbitals of the transition elements project to the periphery of an atom. Periphery means surrounding. Periphery of an atom more than the other orbitals means S and P. Hence, they are more influenced by the surroundings as well as affecting the atoms or molecules surrounding them. In some respects, ions of a given Dn, n may be 1, 2, 3, 4, 5, 6 up to 9. Okay. In some respect, ions of the given D configuration, that is n is equal to 1 to 9, have similar magnetic and electronic properties. with partly filled d orbital. Now partly filled d orbitals, I am telling you, with partly filled d orbitals, these elements exhibit certain characteristics properties such as display of variety of oxidation state. Due to why they are showing this many variety of oxidation state? Because partly filled d orbital, not fully filled, partly filled. That's why it is showing difference many or variety of oxidation state. Formation of colored ions is due to the d orbitals, due to the you can say partially filled d orbitals or incomplete filled d orbitals. This complex colored compound is formed. Formation of colored compound is due to the, you can say, this partially or incomplete filled d orbitals. It is forming colored ions and also forming complex ion. Complex formation is due to you can say partly filled or incompletely filled d orbitals. They are forming colored compound or complex, okay, with a variety of ligands. For the complex formation, ligands are required. Central metal ion will be there. With that central metal ion, because generally it will be transition element, then transition element will have d orbitals. D orbitals are partly filled. Hence, ligands, separate molecules may be ions also, like Cl chloride ion, bromide ion, H2O, Cn. These are called ligands. Okay. Then sometimes carbon monoxide, CO. These will join with central metal ion. Then where it will go? Then it will give their electron to the d orbitals. Vacant d orbitals are there. They are lagged behind the electrons. Then these ligands will make a bond, or you can say it will donate its electron to the d orbitals and complex will be formed. And if you can say ligand, this d orbitals are, suppose these things single electron, unpaired electron. When complex will have unpaired electron, then it will show magnetic properties, particularly paramagnetic properties, and compound will be colored depending on how many, you can say, half-filled electrons are there. Half-filled d orbital, half-filled means I am talking about how many unpaired electrons are there in d orbitals. Correct? Depending on that and frequency of light, because during the transition forming the complex, ions will go to the d orbitals. Electrons will go to the d orbitals. Then that time some energy is involved, and energy involved means it is related to light. Then how much energy is involved means what was the frequency of the light. And every frequency has some color. That's why compound, what type of color is there depends upon how many, you can say, unpaired electrons are there. Correct? How much energy it has absorbed. What was the frequency of energy? Depending on that, it will show the color. And paramagnetic properties. Paramagnetic means it can be magnetized soon. Then that also depends upon this number of unpaired electrons. If it is fully paired, if d orbitals are fully paired, two electrons are there, then that will be dimagnetic. Means it will be you can say non-magnetic, dimagnetic. but if it is a unpaired electron, unpaired orbitals, single electron, then that can be magnetized. That's why it is called paramagnetic. Question is asked, I have given the concept. Okay. Then I told you that with partly filled d orbitals, these elements exhibit certain characteristic properties such as display of variety of oxidation states, formation of colored ions, and entering into complex formation with a variety of ligands. The transition metals and their compounds also exhibit catalytic properties and paramagnetic behavior. All these characteristics have been I will tell you this in details later on. Okay. There are greater horizontal similarities. There are greater horizontal similarities in the properties of the transition elements in contrast to the main group elements. However, some group similarities also exist. Okay. Now, actually, we will go in details, but here one question I want to tell that is actually asked in examination. Okay, already I have given the concept, but question is there. That's why I am telling you on the explanation. I think now we will quickly understood. Can understand very quickly. Question is, on what ground can you say that scandium, means Z is equal to 21, atomic number is 21, is a transition element, but zinc is not. Z is equal to 30, atomic number of zinc is 30. Then on what ground can you say that scandium is a scandium means Z21 is a transition element, but zinc is not? Then already I given explanation. Again I am telling you, on the basis of incompletely filled 3d orbitals, in case of scandium atom, in its ground state 3d1, it is regarded as transition element. On the other hand, zinc atom has zinc atom has completely filled d orbitals 3d10 in its ground state as well as in its oxidized state. Hence, it is not regarded as transition element. Okay. Then this I have discussed about the electronic configuration. Okay. Next class I will discuss physical properties. Today I am stopping only here. Thank you.